Hello, and welcome to Lesson 8 of this Introduction to Calculus with Wolfram U. Our topic for today is the derivative as a function. So let's begin with a brief overview of today's lesson. So in Lesson 7, you learned about finding the derivatives at particular points for a function. Now, the fact is that you can go beyond that, and the derivative itself can be regarded as a function. So starting with the function, you can find the derivative, and then that gives you another function. And the way to do that in the Wolfram language is to use the function d. So let's say your function f of x is like over here. You can work out the derivative using d, and you get back another function. And now you can plot the function and the derivative on the same plot, and you get back this picture of the function in blue and its derivative in orange. So the point over here is that the derivative is a function just like the earlier one, and you can keep on doing the same process, and that's the plan for today, to talk about derivatives as functions and higher derivatives. Okay, so as a simple example, let's say I ask you to find a derivative of x cubed plus x. So you can work out the derivative using d, that's 3x squared plus 1. And then you can also use f prime x, that's another way to do the same thing. And you can plot the function derivative, and you get back the result, which is the plot for both these functions. Now, the difficulty is that there are many ways to write derivatives, so let's talk a little bit about derivative notation. Some people prefer to write f of x for the function, and then f prime x for the derivative. Others prefer capital D. Some prefer y prime. Some use dy by dx. Some use df by dx, etc. And in fact, mathematicians like to think of capital D and d over dx as being differentiation operators which work on functions and give you their derivatives. And the whole process of calculating derivatives is called differentiation. So there's a lot of terminology over here, but as far as we are concerned, if you know capital D and f prime, that's good enough for you. So here I've got capital D of a function and f prime, and you get back just the same result in both the cases. So for this lesson, if you know D and f prime, that's enough to do all the calculations. Okay, so one issue with derivatives is that they are defined by limits. So if they're limits, and because you can talk about left-hand, right-hand limits, you can also talk about left-hand and right-hand derivatives at a point. So here's a function g defined using the real abs function, the absolute value function, and clearly there'll be an issue at 5 where the sign changes. So if you find the derivatives from the right and left at 5, then what you see is that they are different. So you have a problem because the left-hand and right-hand derivatives at the point 5 do not agree. And if you plot the function derivative, you see that a little more clearly. So that's the original function, and the derivative is 3 on the right and negative 3 on the left. So that's one way in which things can go wrong, namely that the left-hand limit and the right-hand limit do not agree, and you do not have a derivative at that point. So let's talk about differentiability. So a function is differentiable if f prime at a exists for a point a. And of course, if you've got a whole range of values from a to b, then it's differentiable if it's differentiable at every point or every number in that interval. So here's a function. Let's find derivative. Question is, where is it differentiable? Well, the only difficulty would be at 0, because then you have a 0 denominator over here. And in fact, if you work out the left and right hand derivatives at this point at 0, then you do see that they are very different. And in fact, if you plug in 0 into f prime, you get back an indeterminate answer. So here's a function which I just showed you, which is differentiable everywhere except at 0. So the question arises, in what way can a function be non-differentiable? When can things go wrong? So one way that they can go wrong is if you're at a corner. So here's an example. you have the absolute value function times 3, and if you plot it with the derivative, you see that at 0, the calculation and graph both show that you have problem at 0, and so you have a corner over there which leads to the differentiability being lost. So you have a corner for the function, and that's an issue for differentiability. Another thing that could go wrong is that you're at a cusp. So here's a cube root function, and at 0 again, there's a problem because you actually have a cusp. That's a cusp over there, a change in shape, and that's going to cause a problem for derivative. You can see derivative does not exist at 0. A third way in which things can go wrong is if you're at a discontinuity of a function. So here's the function, it's piecewise, and it changes form at 0. So that's the function, work out the derivative, and it's 0 there's a problem. You get indeterminate. If you plot it, you can see quite clearly that everything's fine everywhere except at 0. One last thing that can go wrong is if you are at a vertical tangent. So here's the cube root function again, and if you look at 0, you actually have a problem because you have a vertical tangent over there. So that's the way in which things can go wrong, but for the most part, functions will be differentiable, and if they are not, it will only happen at a few isolated points. Now, starting with a function, you can not just work out its first derivative, like over here, but you can go a step further and work out the second derivative. So the second derivative is the derivative of the first derivative. So if you start with 4x cubed, you get 12x squared, and then you get 24x. And you can get the same result by using d with this notation where it says differentiate f with respect to x 2 times. And you get back just the same answer. So that's a shorthand for computing the second derivative. Here are the plots of all three. There's f, there's the first derivative, and the second derivative. So the point is, starting from a function, you can work out the derivative, then you can work out its derivative, and they are all just as good as functions. Now, of course, you can go on with that, and in the Wolfram language, you can work out the nth derivative for any value of n, whether it be 1 or 2 or 6 or 100 or whatever. So here's a simple function, x raised to 6. You can work out the first 6 derivatives. The first expression over here is just the function itself, and the last one is 720, which means that you're almost at the edge where things are going to start becoming 0. Okay, so here's the plot of the first 6 derivatives. You have the function over here, first derivative, second derivative, etc. So you can see over here that the nth derivative is a function just like the earlier one. Okay, now in physics, there are some special names for nth derivatives. So here's a position function, s of t. And if you work out the first 6 derivatives, they've got names. They are called the velocity, the acceleration, the jerk, snap, crackle, pop. That's first derivative, second derivative, third derivative, fourth, fifth, and sixth. And if you plot them, then just like in the earlier case, you get back a plot, but now this shows you the variation of the position and velocity, etc., as time goes by. So higher derivatives are really quite useful. They occur in physics, they occur elsewhere, and in fact, they are what make calculus so applicable in real life. Okay, so now we are at the end of today's lesson, and what you've learned is that you can work out the derivative not just at points, but for entire functions. And what you get then is a new function. Because a derivative is a limit, you can compute left and right derivatives. Now, if it happens that the left and right derivative is not equal, then the derivative does not exist at the given point. And if it does exist, then the function is differentiable at that point. So you've got differentiable functions and non-differentiable functions which can occur in many ways, like you're at a corner, you're at a cusp, etc. But as I said early on, most functions will be differentiable almost everywhere. Now you can go a step further from derivatives and work out high order derivatives, the first, second, third, fourth, etc. And those are quite useful. For example, they're useful for studying the motion of a particle. So that's a lot of stuff over here. We talked about higher derivatives, left derivatives, right derivatives. That's a whole bag of ideas. And in the next lesson, we'll try and make things look much simpler by talking about the rules for finding derivatives. It might all look a little bit difficult right now, but once you have rules of derivatives, then things will become much simpler. So that's for lesson 9. But before that, we will have problem session 2, and you can take a small quiz, and that should put you in good shape for lesson number 9. But I'll stop over for lesson number 8. I hope you have enjoyed it. Thank you.